I'd like to begin by welcoming everybody to the Nonlinear Analysis Seminar. This is the fall 2021 continuation. We were here in fall 2020, spring 2021, and we move forward. So let me begin by saying it's good to be back with everybody, and I think we can catch up a little bit more after the seminar. But without further ado, let me introduce today's speaker. So I'm very pleased to announce today's speaker. Today's speaker got his PhD from Purdue under the supervision of Richard Hunt and has held various visiting positions at Indiana, the IAS, UCLA, MSRI, the Tata Institute, and is currently a distinguished professor of mathematics at Rutgers University. Today's speaker, Segun Chinio, and he will speak on a local version of Courant's nodal domain theorem. So welcome.
So thank you, Daniel, for this invitation. And I'm very glad to be here. So this work that I'm talking about is a joint work with Sasha Loganov, Elena Malinikova, and Dan Mangubi in Hebrew University in Jerusalem. Okay, so I want to set the stage, and so the object that I'm really looking at will be as I say here, will be a smooth, compact Riemannian manifold where the metric is also smooth. So this I would like to emphasize repeatedly, as opposed to what? As opposed to not being real analytic. So there are lots of theorems in this area where the manifold is real analytic and the metric is real analytic. But here the emphasis is that everything is now smooth, but in reality, you don't even need smoothness. You can get by with some C2 assumptions, and that is good enough for everything to work. Okay. So what is the basic object that I would like to study? Well, the basic object that I would like to study is the Laplace-Beltrami operator. And here you see an expression of the Laplace-Beltrami operator in local coordinates. So square root of G, square root is the determinant of the metric square root. G is the determinant of Gij. And then you have the square root, and this is the local expression in local coordinates. Now, to set the stage, I just want to recall several fundamental facts about this operator before I actually go on to what I would like to say. And so one of the important ways of studying this operator is through the heat kernel. So you look at the associated heat kernel, and then you compute its trace, and this somehow gives you statistical information about the distribution of eigenvalues of this operator. So this goes back to the work of Hermann Weyl and Meenakshi Sundaram and Pleyel. And you do not have to use the heat kernel. There is another way where you can also utilize the wave trace. So you look at the wave operator and then look at that. And this was done in a very famous paper by Lars Hormander. Okay. So what we end up getting, if we actually look at all of this, is the so-called Weyl law, which says that if you look at the eigenvalues, so here U is non-zero, so you look, U is an associated eigenfunction associated to this eigenvalue lambda k, then you end up with the following statistical property, that is the number of eigenvalues less than lambda. So this comes out by looking at the heat kernel, computing the trace, and then applying some sort of Tauberian theorem, Karamata, or whichever. And so this is equal to omega n times divided by this quantity, lambda to the n over 2, volume of m, where omega n is the volume of the unit ball in Rn. Okay. And then there are lower order terms, and these lower order terms depends on lots of things, on ergodic properties for bounded domains, and also on and if there's boundary, then on the boundary. We are not assuming that this manifold has boundary to keep things simple. So in particular, if I look at this and I set it equal to, let's say I set it equal to k. So I look at this number and I set it equal to k. That means the lambda k for the kth eigenvalue, this is equal to k, and I solve for lambda k. So if I write this equal to k and I solve for lambda k, then you end up seeing that lambda k has this sort of asymptotic behavior as k goes to infinity. So lambda k, the asymptotic behavior of lambda k is k to the 2 over n. So in particular, in dimension 2, you will see that when n is 2, this is the asymptotic behavior. Now, there are very deep questions of all of these things which are connected with number theory, which is a very fascinating topic. And I would, at this point, make a plug for a survey which has just appeared a few days ago. It's in the notices of the American Math Society, and it is by my colleague, Fioralba Ciacconi. And it has just appeared like 3 or 4 days ago. And if you look at the last section, so this really, this article, this survey paper in the notices has to do with this emerging field of transmission eigenvalues. But if you look at the last section of this survey, there is work that is described that is joint with Ciacconi and myself of a few years ago, and you'll see some very amazing connections between this subject of transmission eigenvalues and number theoretic things. So this is just a plug for that. Okay. So if you look at an eigenfunction, okay, for a given eigenvalue, then one of the things that I'm very interested in this talk is the nodal set. So it is the set of points in the manifold where UK vanishes. So this is a very complicated set. And I'm also interested in this lecture in the nodal domains. So what are the nodal domains? Those are nothing else but the connected components of the set where U does not vanish. So this is something that I'm less interested in, but it has a very strong bearing also, and very strongly related to this object, of which you will see that the results are pertaining essentially to this object, the components where UK does not vanish. Okay, so these are very delicate objects, and the delicacy of these objects can be seen from a theorem of Uhlenbeck, who showed that if one perturbs this metric, the Riemannian manifold metric G, in some CK topology, you perturb it, then the nodal set becomes a smooth manifold, and the eigenfunctions become a Morse function. So that means every critical point is non-degenerate. And these metrics belong to, they form some sort of set of the second category in this CK topology. So there are, bad metrics also. So it's not that, so in other words, if you perturb the metric by a small amount, it does not mean that the nodal set will also move a small amount. It can move in very bad ways. So you cannot hope to get information about these nodal sets and nodal components by saying, okay, let us make things constant coefficient, make it the Laplacian, I can understand it. And then by perturbing the coefficients a tiny bit, you can then get information for the nodal domains and nodal components for nearby metrics. That does not work. Okay, so you have to be very, very careful when you handle these objects, these nodal sets and corresponding nodal domains. Perturbation is not the way to do it. Okay, So now we come to a very famous global result, which will form the foundation for what I'm going to talk about. And this is known as the Courant nodal domain theorem. So the Courant nodal domain theorem says that if you look at the eigenfunction uk corresponding to the eigenvalue lambda k, okay, so this is the eigenfunction corresponding to the kth eigenvalue, then this eigenfunction has at most k nodal domains. So the set where uk does not vanish, it can have at most k components, no more. Okay, so so the point here is that the proof of this result uses a minimax principle and contradiction. But there's one other ingredient that already comes up and which will play an important role for us a bit later. And that object that comes up is the concept of unique continuation. So unique continuation plays a very important role in this whole theory of nodal sets and nodal domains. Okay. So let's try to give a proof of this, a quick proof. So the idea is that by contradiction, you assume that there are k plus 1 nodal domains. Okay, no, and so they are k plus 1. So I want to show that if I do that, then I get a contradiction. And you take the eigenfunction and then restrict it to each nodal component. So it turns out that in each nodal component, this eigenfunction will have just one sign, because in each component, it's either positive or negative. Okay, and on the boundaries, it vanishes. So the boundaries make up the nodal set, the set where uk is equal to 0. So now you see, you can take a function and concoct a function by taking linear combinations of these guys, aj, so that this function is orthogonal to the first k minus 1 eigenfunctions, simply because you have k constants to determine, and you have k minus 1 equations to solve. So you end up with more constants than equations. So you end up with a non-trivial homogeneous system, and you can therefore find AJs, all of them not 0, for which you can then construct a non-trivial H. And there is a little bit of work. This H actually satisfies the eigenfunction equation. But you see, you have utilized k nodal components in this construction. So this is an eigenfunction, but then H vanishes on one complete nodal set, because you never utilized the lambda k plus 1. And so therefore you have now an elliptic equation which has vanished on some open set. Therefore, this elliptic equation has to be identically 0. And so here you see unique continuation appearing. So H has to be identically 0, but then the way you picked it in these AJs, H is not identically 0. So you have a contradiction. So in some very baby version, you already encountered the use of unique continuation, and this will become very sophisticated as we move forward. Okay. Now, I want to point out that this K, I said that it has at most K components, but it was proved by R.K. Pleyel that in general, the number of nodal components is strictly less than K. And this was improved by Jean Bourgain a few years ago. And so let me just show you the proof of R.K. Pleyel that the number of nodal components need not be exactly K, and you will fall and be less than K. So you improve a little bit on the theorem of Courant. So the proof here I'm sketching for you is in 2D. So for each nodal component omega j, this is the set where the eigenfunction does not vanish, connected component, you apply the Fabre-Cran symmetrization. And if you apply the Fabre-Cran symmetrization to each nodal component, you end up getting, because on each nodal component, it's this function uk is an eigenfunction. it's a first eigenfunction for that domain because it has one sign and it satisfies the equation, and on the boundary of that nodal domain it is 0. So it's a lowest eigenfunction eigenvalue. Lambda k is a lowest eigenvalue for that nodal domain. So therefore, if you apply Faber-Cran to each nodal domain, this is what you get. This is the eigenvalue, this is the volume, and here you get pi sigma square. And what is sigma? Sigma is a number which will appear later, but it is the smallest positive zero of this Bessel function. I mean, it has to do with the fact that when you're looking at a disk, what is the eigenvalue, the first eigenvalue of the disk of radius 1 or something like that, and then you get this number sigma. So this is what you end up. So move this sigma, move this omega j over here and sum over all nodal components. So if you sum over all nodal components, you get the total volume of omega times lambda, and here you get pi sigma squared times k, where k is a number of nodal components by contradiction. So you're assuming that they are exactly k nodal components by Courant. And so if you sum, so here you'll get the volume, here you will get k, okay? So now use the fact that I just said earlier on that there is an asymptotic for lambda k from the Weil law. So use that asymptotic. So if you use that asymptotic from the Weil law and plug it in, then you will see that lambda k is like, if we are in 2D, so it's 4 pi k over volume of omega. That was the asymptotic. So you end up getting this. So the volumes cancel, the k's cancel, and so you end up getting that if the nodal Courant theorem holds at every stage that you have exactly k nodal components, then you must have sigma square less than or equal to 4. But the first zero of the Bessel function is this number. So therefore, you see that you end up with a contradiction. So in general, you will have exactly strictly less than k nodal components. And so this is what R.K. Pleyel's observation is. And so there are even more dramatic ways by which things don't work. And so there is also a theorem of Urakawa, which is related to this next theorem. So the two theorems that I'm stating here are actually related. And Urakawa's theorem states that if you take S3, then there is a metric on S3, so that if you look at the lowest positive eigenvalue, well, the lowest eigenvalue is really 1, which gives you an eigenvalue of 0, constant function. But I look at the next slide. Then in the standard round metric case, these are the 4 eigenfunctions. The eigenfunctions are simply the coordinate functions, okay, x1, x2, x3, x4. So there are 4, but for this metric, it turns out that there are 8 of them. So instead of just being 4, and some of you might recognize this 4 in the work of Kasdan and Warner on the Gauss curvature problem and so on, or the scalar curvature problem. But here, that's not my interest. But here, what you end up getting is that this metric, you get 8 such. So the dimension of the eigenspace is 8 instead of being 4 for the standard round metric. And using these ideas here, Berard, Bergerie, and Bourguignon prove that there are compact Riemannian manifolds with metrics on them, such that if you go far enough along in the eigenvalues, then these eigenfunctions have exactly 2 nodal domains. So instead of having L nodal domains by Courant, they have just exactly 2. So, things really fail dramatically in some ways. Okay, these global theorems, you do not really achieve what the Courant theorem says you can. That's at most. I mean, it can fall much smaller than that, and you can have exactly just 2. Pleyel says that in general you have strictly less than k, but there are examples where it's even just 2 all the way for high enough eigenvalues. Okay. So now I'm interested in the local results. So I have to now state a very famous conjecture of Xington Yao. So Xingtang Yao's conjecture, St. Yao's conjecture says that if you look at this set, which is the set where the eigenfunction vanishes, which is the nodal set corresponding to this eigenvalue, then if you look at the n-1 dimensional Hausdorff measure of this set, okay, it is bounded above and below by the square root of the eigenvalue. It's bounded above and below by square root lambda k. So where does this conjecture come from? So here is one way of thinking about this conjecture. So that if you look at this torus, so to say, then you see the eigenfunctions of this torus are out of the form sine kx sine ly. Okay, so it vanishes on the edges here. And then if you look at, so if you look at the eigenvalue, this will, the eigenvalue is lambda L square plus K square. Okay, just you differentiate in K, in X and differentiate in Y, you get K square plus L square. And you see that the length of, so here is the picture of the nodal set. These are the zero sets. And you see that the total length is L plus K. Okay. And so you see that depending on who is bigger, L is bigger or K is bigger, you see that the total length is of the order of the square root of the eigenvalue. So this is a famous conjecture, and Yao's conjecture was stated for smooth manifolds with the smooth metrics. So he made this conjecture for manifolds M, which are smooth. That means the coordinate functions are, patching functions, so on, they're all smooth. And the metric that is associated to that manifold is a C infinity metric. So under these assumptions, he made this claim that the n-1 dimensional Hausdorff measure is controlled. So it's not, so it's like saying that total length is of the order of square root lambda k, as you can see in this example. So what's known about this conjecture? And so let me explain. Okay, so I just want to also point out that if you combine these eigenfunctions, then the number of nodal components of this sum may be more than each individual one. So here we have, so the nodal components here are these. Okay, so these rectangles, these are the nodal components. So it's possible that you can actually concoct constants and take linear combinations where in the same these have multiplicity. So you can look at the eigenfunctions corresponding to the same m, k squared plus L square equals m, combine them and get more nodal components than for individual ones like what we are saying, Lk or whichever. All right. So the first major breakthrough in the Yao conjecture was by Harold Donnelly and Charles Pfefferman. And so they assume that your manifold is real analytic and the metric is real analytic. Okay, this is very important in their proof. And under this, they show that Yao's conjecture is actually true. Okay, so this is so the question then remains, well, what can one say when M is smooth and G is smooth? So this is around 1990, and for a long period of time there was no progress on this problem. There were results in the smooth case by Bob Hart and Leon Simon, but you see their result is that the nodal set is bounded by something like lambda k to the lambda k to the lambda k. This is huge. I mean, this is so far away. It is like super exponential. Okay, so essentially all that you can really say is that this is finite. That's all you can really conclude from their theorem. There are also results by Nadirashvili in lower dimension dimension 2, where he shows that the one-dimensional Hausdorff measure is bounded by lambda k to the 3/4. So this is a theorem of Nadirashvili about the same time, a few years, maybe 2 years after Donnelly Pfefferman's work. Okay, and that's in the smooth case. So this is what is known in the smooth case. I hope that things okay. Now, so the next breakthrough comes from the work of Logunov and Malinikova, who now actually say something when the metric, the manifold and the metric is smooth, and they prove that the lower bound of Yau's conjecture is now verified. They still cannot really get the upper bound, but they at least have now proved that this upper bound is a polynomial growth. So it's growing. So the instead of square root, I mean, they have lambda k raised to some capital N, but the lower bound is of the order of square root lambda k. So now the question that really remains is, at least, this is one question that remains, whether you can still make it root lambda k. But another question that remains is that, can nodal domains that we have now seen, can they be thin and narrow? So this is analogous to asking whether there is a local Courant theorem. So I will explain this and then tell you what the result is. So what do I mean by local Courant theorem? So we know a global Courant theorem. That so here is what is happening. So the simplest example you can think of is a standard Sturm-Liouville problem in one dimension. So you have yk double prime plus k square yk equal to 0, and then on both boundaries you set it equal to 0. Yes, I said there is no boundary, but this is very helpful. So the eigenfunction is sine kx. So here is the eigenfunction, and here you see that the number of components is just the intervals, and these are the nodal sets, and the intervals where the function does not vanish are the nodal domains. Okay, so you see that there are here there are exactly k nodal domains. So here you have exact Courant's theorem, but this is global. But now you see, if I take a point like this and I take a tiny interval, then I see that instead of k nodal domains, I have actually 2 nodal domains. So in pieces around it, in small regions around it, I don't see k, but I see much less than that. I see just 2. Okay, and there is a certain scale. If I take a bigger scale, then I begin to see more. So this has something to do with the fact that whether nodal sets, nodal domains are thin and narrow. Okay, so this will become a little bit more clearer when I go and when I look at this picture in 2D. Okay, now you have a similar picture in 2D. Okay, and so what I do is I do the most obvious thing. I separate variables. So I look at FR H theta, plug it in here. I get a differential equation, which we all know is some Bessel differential equation. And this is essentially the picture of the nodal set. So you see, you get this sort of pizza picture. And here you see that in 2D, that the number of local components is roughly of the order of square root lambda k. Okay? And in one dimension, we saw that the number of nodal components, when we looked at the little interval, is like a constant. But in 2D, it becomes square root of lambda k, because you get this pizza pie peak. So these nodal domains, so here is a local, this is a local picture, and these things can go and then wind around and come back and join. But in the local thing, you see one nodal component can actually be a separate nodal component than this guy. Okay, and here, what is the scale in which I discover such a thing? Well, the scale in which I discover this thing is like 1 over root lambda k. This is the scale. Okay, so what's really happening? So here you see I have a ball. Okay, that's my microscope under which I'm looking at the nodal domain. And here there is one global nodal domain. Now this global nodal domain goes in and out of this ball many times. Okay, and it could in principle be very thin and narrow, like this red thing. It's very thin and narrow, and it goes in deep inside this. Okay, so the question is, can I count in if I take a ball, can I count how many nodal components there are in this ball? Okay, so here is one such nodal component. Now, obviously, you have to be a little careful when you pose this question, because I can take a ball and I can just I can just look at something that goes a little bit inside. I'm not interested in this. I'm interested in those nodal components that go and hit the middle half of the ball. So I have a ball and I am interested in the set where u is not zero, those components where u is not zero, that is intersecting at least intersecting the middle half of the ball. So anything like this, I'm not counting that. I'm not counting these. I'm only counting these. And of course, if it is inside, okay, that is also being counted. So if you have lots and lots of them, okay, like you have long, thin, narrow ones, lots of them, then there would be some sort of trouble. And I want to say that this sort of behavior does not happen. So how can I eliminate this sort of behavior? By actually counting the number of such components. And so you see here, this is also connected with Yau's conjecture, because if it is thin and narrow, then if the nodal set goes in and out many times, it will build up in its length. So the length also will increase. So if I show that this sort of thing does not happen, then it is also some sort of hinting that, you know, this result of Yau is the right sort of thing. So this question was raised by Donnelly and Pfefferman also in 1989, 1990, and they have a result. But let me just indicate a theorem that was proved very soon after that by Ben Markenhoff and myself. And the result is the following. So you take everything smooth. So everything now is smooth. And you take one nodal component that intersects the middle half of a ball. So you have this ball, and you take this one component that goes and hits the middle half. Then the volume of this shaded portion divided by the volume of the ball. So this the fraction of this to the volume of the ball is bounded below by lambda k to the minus 2n square, minus n over 2, and then there is a log factor. So you can just ignore the log factor essentially, because, you know, this is the real factor that's at work here. Okay, so what does this do? Well, let's do what we did earlier. You sum that inequality on both sides. So on this side you have the volume of the ball, and this side you have B, and then if you sum, you get the total number of nodal components that hit the middle half of the ball, capital N. And so the B's cancel, and it turns out that N is that, okay? And if you use the while law, you see that the number of nodal components is no more than k to the n squared. Okay, so it's you see it's k globally from Courant, okay, and locally it's turning out to be k to the n squared. But then from our examples, if you look at a small enough thing, it should be like in 1D, it was a constant. So this is not the best result, as you can see from the here, sorry, I made a mistake. This n is like this n is like k to the n. So this is what we got. We got k to the n, but Donnelly and Pfefferman got k raised to the n squared. So their work, you got k raised to the n squared, and from our work it's k to the 4n. But both these are not the right result. I mean, it's not. It's a long ways off from being the right result. I mean, you don't even get the Courant theorem from here, okay, the global result. Leave alone the fact that locally, it seems you should be able to do much better. So before I proceed, I just want to point out that there are uh, two ingredients that are needed in this proof. One is what is called nowadays, it's a big area, a quantitative Kármán inequalities. So you want to do unique continuation. What do you do in unique continuation? You have some elliptic equation. You assume that U vanishes to infinite order. And then if it vanishes to infinite order, then it vanishes identical. But here what you want to prove is that you don't need to assume it vanishes to infinite order. You want to say that because it's an eigenfunction, if it vanishes to order square root lambda k, then it vanishes. So these are called quantitative Kármán inequalities. So unique continuation with precision. Okay, so that's one tool. And the second tool that is used is some sort of combinatorial tools involving covering lemmas and so on. So these are the ingredients that went into our proof. And it was in here that we made several improvements. So here we did not make many improvements. We used the quantitative Kármán inequality of Donnelly and Pfefferman, but here we made a covering lemma improvement, and that was very crucial. So what is the conclusion of this Kármán inequality? The conclusion of these Kármán inequalities is the following doubling condition. So what we proved was that if you take UK square and you do an integration over a ball of radius delta, which has been dilated by this factor, which is the eigenvalue, okay, then this is controlled by the integral of the UK square, the eigenfunction on a ball of radius delta. So eigenfunctions, essentially you can pretend that they are polynomials of degree root lambda k. So, you know, if you want to think of a model, then you can think that eigenfunction is a polynomial of root lambda k. And essentially this is what the quantitative unique continuation theorems or the quantitative Kármán theorems are sort of telling you. So in addition, there was this covering lemma which appears in our paper, which is a interesting lemma because it's an improvement on the standard Vitali lemma that you learn in measure theory courses. And so the lemma was that if you take E and it's written as a finite union of balls, you can take a finite union, then what you want to do is you want to extract from it a disjoint union. And you can do so, but then you see you have to dilate this disjoint union by a factor of 5 or something like in Stein's book, and then say E is contained in a factor of 5 of these balls. But for these purposes, because of the nature of what is going on here, you're not allowed to dilate by 5. And so what you're allowed to dilate is by each radius by 1 plus delta. That's all. And so you have to pay a price. So you can take E and it will be contained in the union of Bxrj, the Rj is the radius of this ball, 1 plus delta. But the price is that it will not, the balls will not be disjoint, but will have control on the number of overlaps, and they will not exceed delta to the minus n. So this is the point of this covering lemma, that if you are not allowed to dilate up to 5, then yes, you can still cover, but then the balls will be almost disjoint, and there will be a control on how many overlaps you can have. So this, along with the unique continuation, was very useful, and it allowed us to prove the fact that if you take the absolute value of UK, take the logarithm, then there is a control on the DMO bound, and it grows like this. And this is not the best way, because as I pointed out to you, that UK behaves essentially like the square root of lambda k. So this thing here, lambda k to the n, is not very good. It should be, the optimal bound should be root lambda k. That should be the optimal bound, because after all, if you have a polynomial, how do you detect its degree? Well, if you have x to the alpha and you want to detect the alpha, what do? You take the absolute value and take the logarithm, and then the alpha comes in front. But then you have log of absolute x. So you have something like log of absolute x and alpha. So you want to detect this log absolute x. So what is a good space to detect that? Well, BMO. If you take the BMO norm, then this alpha will come out, and the norm of this in BMO is some constant. So this is, you should think of this sort of reasoning to as a way of detecting the degree of the polynomial which this eigenfunction is supposed to mimic. And it should be root lambda k, and so you see that this is quite far from root lambda k, and so there is a problem. Now, these methods that I described to you were pushed a little bit further by my student in his thesis, Goshan Lu, and so but they are, like, what you could do is this n, just replace it by n minus n epsilon, very tiny improvement. Okay, so there was a big problem, and so for all this time, the optimal local Courant theorem that I'm trying to drive at for the smooth case, people had done it now for real analytic by now, but for the smooth case, I mean, the attempts were mainly unsuccessful. Let's put it this way. I mean, there might have been attempts by other people I'm not aware of, but more or less they are unsuccessful. So now we come to the result, and here is the new theorem. And so what I'm trying to say here is that if you have a nodal domain, okay, so in other words, if you take a nodal domain which is contained in B2R, so you take the component which intersects B2R, and such that the nodal domain also intersects half the ball, exactly the situation as before, then it turns out that the volume of this is bounded below by this quantity. So this looks a little crazy. R is the radius of this ball. So it is actually optimal, because it turns out that the number of connected components of the nodal domains that intersect BR is bounded by this for big balls. And when the ball comes down to a certain scale, it's exactly k raised to the n minus 1 over n, and that is optimal. You see, this number is exactly in dimension 1, it is k to the 0, which you saw, you got 2. In dimension 2, this is a k to the 1/2, and that's exactly what we saw. And that is exactly the situation in all dimensions. So you see here that this bound is now even less than 1. So in locally, you're even better than the global Courant theorem. And as the ball becomes bigger and bigger, then this term begins to dominate. And there you see that in the ball becomes the same or about the same volume as the volume of the manifold, then you see you get K. So you get K for very big balls, which is the global Courant theorem. For tinier balls, you get K raised to the n minus 1 over n. So you get an improvement. And then there is a certain region of transition where these two are going to be roughly the same. And so you can compute what is the radius of the ball when these two quantities are the same. So this is now the end of the story, okay, except that we do not know these constants. Of course, I mean, in the global Courant theorem, essentially, you know that this constant is like 1. But here we do not know these constants. But as far as the growth is concerned, this is the optimal growth. Okay, so this is our result. And so the idea in the proof is again, we are making use of quantitative unique continuation, and that is very important in our proof. And what we don't use BMO anymore, but the spirit of BMO is very important still. And so one ingredient that's used is this inequality, which is coming out of it is very similar, you see, to this BMO type of result. Here you see the square root lambda. And if you are very familiar with the theory of A infinity weights of Markenhoff, then you will recognize that this is more or less morally something that tells you that the log of U is BMO with a BMO norm not exceeding square root of lambda. So this is sort of, these two things are related. And what I'm saying here is that if you have control, you have a set E which is contained in a ball, then the supremum of U on that set E essentially controls the supremum of U on that ball, and you have this factor in front of you. Okay, and the exponent in front is essentially related to the BMO norm of log U. And the fact here is that more or less this is like saying, as I pointed out, that eigenfunctions behave like polynomials of degree root lambda. That is a guiding principle in all this. Okay, so so I think what I would like to do now is stop here. I think this is a good place to stop. I want to thank you once again for this invitation, and it has been a pleasure giving this seminar. Thank you.
Thank you very much for your wonderful talks again. Are there questions? I saw one question I'll mention there. Will these lecture notes that you have? Oh, I'm sorry, go ahead.
Yes, go ahead. I mean,
one question I saw mentioned on there is, will these lecture notes that you've went through, will they be possible to share with some of the audience somehow?
Yeah, the actual paper is on archive already, so I can you know, you have, I think, made a recording. Right?
Yes.
So you should have a copy, right, of the notes, I would think.
Okay. Okay. We'll see
Right?
if
I have one question.
Yes.
Yeah. Sir, I wanted to ask, can this be related to partitioning problem? Like,
I really don't know. I haven't thought about that, but it's possible that it's related to partitioning problems. It's an interesting question, but I really haven't thought about it. You know, I haven't. You know, my focus all these years was to solve this problem. You know, and as I said that the result of Markenhoff and myself was k to the 4n.
Yeah.
So the point was to actually break the Courant bound. You know, I mean, well, the point was actually to get a bound which is k to the alpha. Alpha does not depend on n. So, for example, alpha is 1, it would be fine.
Okay.
So even that, to get there for smooth case, okay. For real analytic, I think the Mangubi probably had a paper that he could do. He could get the good bounds or something. I'm not sure. He might have a paper. But the question then is that could you get it? And so now not only do you get it, but you actually get the one which is optimal, because alpha turns out to be n minus 1 over n. And as you saw, let's say in dimension 1, yeah, so that's like k to the 0. In dimension 2, it's k to the 1/2, and you can. I mean, I just gave you these examples in 1 and 2, but in the paper you'll see that we actually show that's optimal in all dimensions.
Okay.
I mean, I just said 1 and 2 in so
Yeah.
as to give you some motivation, for a seminar. But in the actual paper, k to the n minus 1 over n is optimal in all dimensions, and of course n minus 1 over n is strictly less than 1. So you break the one, the not only have you break the Quran bound, but you actually get the sharp bound.
Okay, fine. Yeah. Thank you. Thank you.
Other questions?
Yes, hello.
Yeah.
I just want to ask you, you said for perturbations, the nodal sets are not stable, but I want to ask if there's any differential equations for the perturbation where the nodal domain is stable.
I mean, you're saying that, can you find, is there a family for which perturbations makes things still stable? Is that what you're asking?
Yes.
I don't know. It might be very difficult because there is no direct link between the coefficients and the zero set. This is what is the problem. I mean, you see, it's not, so you can say regularity and the coefficients, there is a link, but there is no direct link. I mean, you might want to say, okay, I do a Taylor expansion and so on. But already you're seeing that, I just need very minimal amount of information here, C2, to make these things, or maybe C3, something like that, to make this theorem work. So I really didn't need smooth here. It's just enough to get the Carlemon inequality. That was enough for me. So I'm very doubtful that you can keep track of the nodal set in terms of the perturbation of the coefficient, freezing it and so on, like a Schauder theory. I think it would be just impossible.
Okay, thank you.
Other questions? Did you have another covering lemma that you were thinking about going through that was covered up at the end?
No, I mean that covering lemma is in the paper with Markenhoff. It's from 30 years ago. I don't think it has been used for anything other than that work. Nobody used it after that. I mean, my student just managed to improve that lemma a tiny bit, and then, but then it doesn't really do much because, like I got k to the 4n something, and then he gets probably k to the 4n minus epsilon. So it's, you can improve it, but in the end, there is something more that's needed. So that was it. I mean, I don't know whether there is any more use of that covering lemma. It was created for exactly this problem, maybe, and then nobody else found any use for it. And now, with this result, I probably the covering lemma dies. But it was interesting, to get this sort of covering argument.
Thank you. I'll ask you a little more afterwards. So if there's no further questions, we'll thank the speaker again.